Hi students, welcome to Practical Science. Today what we're going to do is have a look at a double displacement reaction. Now a double displacement reaction is also called a precipitation reaction. It involves two solutions, and when they mix, one of the components or one of the compounds that forms as a result of those two components will actually form a precipitate. That is, a substance which does not dissolve in water, and we'll actually see that come out. So what we want to do today is we want to continue to use our understanding of the mole concept to weigh out each of these salts very carefully and to create a precipitate, which again we're going to filter and then carefully weigh. So let's get into it. So let's have a look at what we're going to be using today. The first thing is our old favourite, copper sulfate. So we're going to make a solution from the copper sulfate. But we're also going to make a second solution today. And the second solution is going to be sodium carbonate. Now, one of the things that we will talk about are the solubility rules. That is, how do we determine whether a particular salt is actually going to dissolve in water? Well, we're going to look at a series of rules called the NAG-SAG rules. And this helps us to get a bit of an understanding of which types of compounds are soluble in water and which are not. And so that means we can get a bit of an idea about what sort of things we might expect when we put these two substances together. So here are our two substances, sodium carbonate and copper sulfate. And here is our NAG-SAG. So for those of you who haven't learnt solubility rules yet, all nitrates are soluble. All ammonium salts are also soluble. The first G refers to group 1 in the periodic table. These are the active metals: sodium, potassium, rubidium, and so on. All of these group 1 metals, when they form salts, form soluble salts. S is sulfates. Now the sulfates have a little double asterisk, and I'll tell you why in a moment. The second A is for acetates, and all acetates are soluble. And the second G stands for group 7, or sometimes group 17. And these are the halides. So the halides are the things like fluorides, chlorides, bromides, iodides. These are also soluble, but they likewise have a little asterisk. One asterisk stands for LMS. LMS is lead, mercury, and silver. 2 is LMS and castrobare. The castrobare is calcium, strontium, and barium. So what this means is that all sulfates are soluble, but lead sulfate, mercury sulfate, silver sulfate, these are not soluble, they're insoluble. Calcium sulfate, strontium sulfate, and barium sulfate likewise are insoluble, but all other sulfates are soluble. For group 7, the halides, all halides are soluble, but there's a small number that are not. The lead, mercury, and silver halides, so silver chloride, for example, would not be soluble. It would be insoluble. So let's see if we can now figure out what's going on in our experiment. Sodium carbonate, well, sodium is a group 1 metal, and we've said the salts of group 1 metals are soluble. So therefore, sodium carbonate must be soluble. What about copper sulfate? Now we've said that sulfates are soluble, But there's a number of exceptions, and the exceptions include lead, mercury, silver, calcium, strontium, and barium. Now, copper is not one of those exceptions, which means copper sulfate is also soluble in water. But what happens when we mix these together? When we mix these together, what we do is we create what's called a double displacement. So previously in our single displacement, we had one cation pushing out the other cation from the solution. In that particular case, we had the very active metal magnesium displacing copper from the solution. However, in this case, we've got a double displacement. So in effect, these two cations are going to swap partners. Sodium is going to go with the sulfate ion and copper with the carbonate ion. Now the thing is, all of these ions are in solution. So you can also think of it as all species are available, 2 lots of cations and 2 lots of anions, and then they kind of shuffle themselves out into whichever of those is the least soluble in water. Now, for the reasons that we already discussed, sodium with anything is going to be soluble. So anything we see is likely not to be sodium. But what about the copper and the carbonate? Copper doesn't fulfill any of the NAGSAG requirements, but neither does the carbonate. So let's see what happens. Now, if we want to mix these two together in order to find out what actually happens in this particular reaction, then we need to sort of figure out how much of each we're going to put together. Now, it would make sense if I measured out 2 grams of each of these 2 salts and mixed them with water. The only problem with that is that we do know from our periodic table that not all substances weigh the same amount. So 2 grams of a very light element would give us a lot more in terms of moles than 2 grams of a much heavier element. And that means we need to take into account the molecular mass of each of these compounds before we do our little calculation. So the first thing that I wanted to do is to grab a small amount of the sodium carbonate. So let me transfer that to one of my beakers. Okay, so now I've got my 1 gram of sodium carbonate. Now I'm going to put an equivalent amount so that I've got a consistent mole ratio for my copper sulfate. But in order to do that, I'm going to need to use 1.5 grams. 1.5 grams. Of course, the exact values are not critical. The main thing is that we write each of these down. So I have sodium carbonate, 1.00 grams, and copper sulfate, 1.50 grams. So let's transfer that to the second beaker. So now we have our 2 solids, our sodium carbonate and our copper sulfate. But I can't just mix these together. I said in the beginning that if we're going to do a double displacement, we need to mix together 2 solutions. This means we need to add some water. So I'm going to measure out using, this time, my measuring cylinder, 5 mils of water. I'm just checking the bottom of the meniscus because I want the bottom of the meniscus to line up with the 5 mil mark. So there's my first 5. So it's going to go in there, and then we'll do the same thing again. I'm checking the bottom of the meniscus. I always want to make sure I'm looking straight on because I want to avoid parallax error, being nice and accurate. So there's 5 mils into my copper sulfate solution. Now we want to try and make sure that as much as possible we've mixed them in. So we've got most of these dissolved. How good is that? Now that is a precipitate. Look at that. That is a beautiful precipitate. But you know what? We want to try and get that out of there. So in order to do that, in order to have a look at exactly what we've produced, we're going to need to filter it. Now we've done filtering previously, we did that in one of our earlier videos. So let's see exactly what this precipitate looks like. So if we're going to carry out a filtration, we need to make sure that we've weighed our piece of filter paper. It's a little bit windy today, so I'm just going to see if I can get this to work. So 0.33 grams. Time to do our filtration. So I think most of this is finished filtering now. So what we want to do is now we want to dry it out. So let me just take it over. There's one I prepared earlier. So it's already started to dry out a little bit. And now we've got our second one. So we're going to leave these sitting here. And we want the water to evaporate so we can then have a dry weight rather than a wet weight. So let's give them a little bit more time. So we've let these settle for a little while. We've actually had to bring them inside because it's been such a windy day that we didn't want any of the precipitate to blow away, which would be a very important source of error. So what we're going to do is we're going to turn on our little balance, electronic balance over here. So I'll put on the first. So here's the first one, 0.91. You can see that the precipitate doesn't look anywhere near as impressive now that it's dried out. And here's the second one. Now, if you notice the second one, it looks still like it might be a tiny bit damp at the edges. So that's a possibility, but let's just record that anyway. So the second one is 1.08. Now I've kept my original values. And that's why I write them in my book, so I won't have to remember them. So that means if I subtract the filter paper, we've obviously had to go to a second filter paper. The first one was just getting too clogged with the residue, so I had to switch it over. The other thing that you will notice is that we did collect the filtrate. The filtrate's had a little bit of time to settle now, and you can see there's a slight blue coloring in there, and there's actually a little bit of precipitate still down the bottom. So some of it's actually gone through the filter paper and it's caught in the bottom. So if I was to do this with a little bit more precision, then what I would need to do is to refilter both of these and collect more of that residue and wait for my final weighing until I've got rid of all of that. In episode 4, we're going to be looking at an evaporation step, and we're going to see if we can recover the other compound that we formed in this double displacement reaction, which is the sodium carbonate. Now obviously if we want to do that, we're going to have to remove the copper out of this first of all, but we'll do that in our next video. For now, let's have a quick look at these numbers. So here's just a little bit of scribbling. I've subtracted, so these are my two values. I've subtracted the mass of the filter paper, which gives me the mass of the residue in each case. So here's one value and here is the second value. I've added these two together and I now have 1.33 grams of copper carbonate. So I can convert that to a number of moles by again dividing the mass by the molar mass, and that will tell me how much of my actual copper carbonate I've recovered. I can use my theoretical values from the original part of the experiment to actually see my degree of accuracy. Now, if I'm not spot on, there's two possibilities. One is that I am too low, which means that I haven't recovered all of the copper carbonate, and there's a suggestion from the color of the solutions in the filtrates that that is the case. But it could also be too high. And if it's too high, then there's two possibilities. One, that some of the sodium and/or the sulfate has actually crept into the residue. But it's also possible that I haven't fully dried this, and therefore there's actually a weight of water that's part of this final mass. So we'll look at the calculation and we'll see exactly what that value is. So what we've recovered when I do the calculation over here, and to do this particular calculation I need my periodic table. I've got the molar mass of copper is 63.55, the molar mass of carbon is 12.01, and then I've got 3 oxygens, so I've got 3 lots of 16. So I add these together and I get a molar mass of 123.56. And then I have my mass divided by the molar mass, which in this case I've worked out to be 1.33 grams of the residue divided by the molar mass to give me a final number of moles of 0.01 moles. Now this is slightly more than the calculation which I've reproduced here for you, just slightly more. Some of it is what we might call within experimental error. However, the fact that it is a little higher suggests that maybe there is still a little bit of moisture that is left in our residues, as you can see. And because we've also got a little bit of the copper ions in the filtrate, then clearly that filtrate has copper still in it. So that means that copper has not precipitated out of there. And indeed, there looks like a little bit of residue in the bottom. So we've got a few little sources of error. There are a couple of other things you may have picked up along the way, including the fact that both of these are hydrated forms. So you'll notice that both the copper sulfate, which we've looked at previously, a pentahydrate, and also the sodium carbonate, which is a decahydrate, so 10 water molecules locked up, and we didn't take those into account when we were doing our calculation of moles. So that again could be a source of error. Any residue that you might see on our little working space could also be a potential source of error. And as we've mentioned previously, we're working with very small volumes, very small masses, and so therefore small errors can be magnified when you're only using small quantities. So all things considered, not a bad result. So there it is, episode number 3, double displacement reactions, also known as the precipitation reaction. We produced a beautiful precipitate of copper carbonate, really fantastic. Have another look at the formation of that earlier in this video. That was a great precipitate. But we haven't quite been able to get the exact bang-on results that we would have expected. But this is science, and sometimes we need to review our processes, we need to look at our procedures, and we also need to repeat our experiments. Because we want to give you a little bit of an idea of not only how to do these particular reactions, but also the process involved and the calculations associated with those chemical reactions. That means we want to make sure that we give you a little bit of an overview rather than going, I'm not going to publish a paper on this, so therefore I'm not going to repeat my experiment, which would be good experimental practice. The values that I calculate are based on the mole ratio of 1 to 1, And the precipitate that I identified was identifiable both from our NAGSAG rules, but also from the color of that precipitate. The fact that it was a very blue color, and also, if you remember from previous videos, that darker blue color of the copper sulfate was an indicator of the presence of water molecules. So it's very highly likely that that slightly higher mass than what we were expecting for our precipitate may be a result of water that's present in that precipitate still, without it completely drying out and the water disappearing. That's it for double displacement reactions, our third in this series of practical science. Thanks for watching.